Okay, Nish, if you want to get us started, go ahead.
Okay, sure. Thanks, Masha. Um, Welcome all. Um, Today's webinar will be given by Kyle Shackelford, who's a graduate student at CSU with Charlotte DeMott and Peter Jan van Leeuwen. Thanks, Kyle, for accepting our invite to give the webinar. Kyle will talk about rain layer formation dynamics and its feedback to the atmosphere. So take it away, Kyle. Thanks.
Okay, thanks, Anish. Go ahead and share my screen. Yeah, so today I'm going to be talking, I'm very excited to share this work with all of you. And thanks again for having me here to talk. So I'm going to be talking a bit about Indian Ocean rain layers and their feedbacks to atmospheric convection within the context of the Madden-Julian oscillation, as well as how they regulate the exchange of energy between the atmosphere and ocean. And this is work that I completed alongside my advisors, Charlotte DeMott and Peter Jan van Leeuwen at Colorado State, and also with our collaborators, Matt Maslov and Ray Sun from Scripps. And so today I'm going to be talking about rain layers. So precipitation that's falling over the tropical warm pool is colder, fresher, and less dense than the ambient ocean water. So under low to moderate winds, this can stabilize the upper ocean and form a stable rain layer. So in this kind of crude schematic on the right, you can see rain layers feature an unstable temperature profile, but a stable salinity profile. And these features are able to persist on timescales of hours, sometimes a day or more, because the magnitude of stabilization and the salinity profile is typically much, much greater than the destabilization and the temperature profile. Rain layers shoal the ocean mixed layer base, which confines evaporative cooling to the near surface rain layer, and it also reduces subsurface ocean mixing below the rain layer. So within rain layers, you tend to have reduced sea surface temperature and sea surface salinity. The reduced sea surface temperature in rain layers can influence turbulent heat flux, and the stability and shoaling of the ocean mixed layer depth that occurs within rain layers tends to decouple the subsurface ocean below the rain layer from the atmosphere above, which we'll later see can have impacts on convection within the context of the MJO. And so when we think about where these might be forming, we can actually see some evidence in satellite imagery over short-term and climatological means that the warm pool region tends to feature reduced sea surface salinity, especially compared to the rest of the tropics. So here in this 8-day mean 2015 taken from SMAP, you can see reduced sea surface salinity over the tropical warm pool. Similarly, in this annual mean taken from Aquarius from 2011 to 2015, you can also see this reduced sea surface salinity signature over the tropical warm pool. And this is partially due to the fact that this region receives significant rainfall in addition to river runoff and other factors. And so one reason we want to investigate this is because the influence of rain-driven changes to ocean temperature and salinity profiles on air-sea interaction and atmospheric convection was pretty unclear. So this figure here is showing on the left a animation of rain rate, and on the right an animation of sea surface temperature from some coupled ocean atmosphere model simulations we conducted that I'll be talking about in depth throughout this presentation. And what you can see is the areas that are featuring heavy rainfall on the left tend to correspond to reduced sea surface temperature on the right, as well as a sharpening of SST gradients and just adding some texture and contrast to the SST field. So going into this, we really thought that the SST gradients associated with rain layers may imprint on the atmospheric boundary layer through pressure perturbations and drive low-level patterns of convergence and divergence, which could potentially trigger atmospheric convection. But in our simulations, we found that there was not really a lot of evidence of this occurring. So I won't be talking about that too much today, but if you have any questions about that, I'd be happy to answer them. And so interactions between the rain layers and the atmosphere are pretty complex. So this diagram here is kind of showing some of what we expected to see and what occurred in our coupled simulation. So again, rain layers feature reduced sea surface temperature and sea surface salinity. They tend to shoal the ocean mixed layer depth to the order of meters, and this confines evaporative cooling in the statically stable near surface rain layer. Below the rain layer, you have reduced ocean mixing. The reduced sea surface temperature within the rain layer locally reduces turbulent, latent, sensible heat flux into the atmosphere, which can hinder the local development of atmospheric convection. And additionally, because rain layers show the ocean mixed layer base, you have penetrating shortwave radiation that can penetrate below the rain layer base and heat the subsurface ocean, which is effectively decoupled from the atmosphere. So that heat can kind of build in the presence of a rain layer until the rain layer is ultimately destroyed by wind-driven mixing. See, these are some of the ways we thought rain layers may impact air-sea interaction. And so, like I said, we're interested in looking at the feedbacks, rain layer feedbacks to atmospheric convection within the context of the MJO. And so today I'm going to be talking about the MJO across three distinct phases, being the MJO suppressed phase, MJO disturbed phase, and MJO active phase. So you can kind of see those outlined on this diagram here, taken from Benedict and Randall. From the atmospheric perspective in the MJO suppressed phase, you typically have large amounts of downwelling shortwave radiation impinging on the ocean surface. You have low winds, and you tend to have infrequent clouds of precipitation. So during the suppressed phase, we don't really anticipate rain layers to be forming too often. On the other hand, during the MJO active phase, you have well-organized deep atmospheric convection. However, you also have very strong winds. So this is another period that we don't expect rain layers to be forming too frequently, because typically the winds are just too strong that any freshwater input on the ocean surface is pretty rapidly mixed throughout the column. And it's really this disturbed phase, or the transition phase, as the MJO gradually transitions from convectively suppressed to convectively active conditions. You have gradually building clouds and precipitation, but you still have relatively calm winds. So it's during this period that we really expect to see rain layers form and expect to see their direct feedbacks to MJO convection to be most evident. And like I hinted at, the way we investigated this was through coupled ocean atmosphere model simulations. So we used the Scripps Cost Regionally Integrated Prediction System, which is WRF, coupled to the MIT GCM. And we conducted 1 month simulations of the November 2011 MJO event that was observed during the Dynamo Field campaign. So you can see our 10 by 10 degree grid in this figure on the right, outlined in red. And I'll also point out that this smaller orange square in the center of the domain is just a 1 degree by 1 degree subdomain that I'll be showing some stability profiles from later on in this presentation. And our simulations feature 2 kilometer horizontal grid spacing, as well as 10 centimeter vertical resolution in the upper ocean, so we could resolve the fine scale features of rain layers in the upper ocean. And we conducted 2 simulations to assess how rain layers influence atmospheric convection. The first simulation was the RL, or rain layer simulation, which can be thought of as a control experiment of sorts, where we just conduct a fully coupled simulation. In the second simulation, the no RL, or no rain layer simulation, we conduct a mechanism denial experiment in which rainfall that's generated by WRF is not passed to MIT GCM as surface forcing. So you don't have rain cooling and freshening in the upper ocean. You don't have rain layers forming in the no rain layer simulation. So the 2 simulations have the same initial conditions in boundary forcing, but you just don't have rain layers forming in the no RL simulation, whereas in the RL simulation you do. And so the idea is we can kind of look at some domain mean changes between these 2 simulations to assess how rain layers influence air-sea interaction and MJO atmospheric convection. And so before getting into the results, these figures are just showing animations of rain rate early on in the simulation for the rain layer simulation on the left, no rain layer simulation on the right. You can see from the large scale, they look pretty similar, but if we zoom in, you can start to see some small scale differences in the organization and the intensity of atmospheric convection. And this is for the second day of our simulation. As the simulation goes on, some of these differences become more apparent. And even quite stark at times. Similarly, with SST over the same time period, you can see for the no rain layer simulation on the left that rain layer features are somewhat evident as regions of reduced SST, whereas in the no rain layer simulation on the right, you tend to have a smoother SST field. So while these two animations look fairly similar from the large scale perspective, the effect of rain layers is to locally reduce SST, enhance SST spatial gradients, and add contrast to the SST field, as we can see here. Okay, and so initially kind of looking at how atmosphere and ocean characteristics tended to vary across our simulation as a function of MJO phase, these time series are showing domain mean variables over the smaller subdomain that I pointed out earlier for from top to bottom rain rate, wind speed, downwelling shortwave radiation, the temperature component of the buoyancy frequency in the upper 4 meters of the ocean, the salinity component of the buoyancy frequency in the upper 4 meters of the ocean, and then the overall buoyancy frequency. And I'm just going to quickly step through what characteristics are of each of the individual MJO phases that we're going to be talking about. So during the MJO suppressed phase, you tend to see infrequent rainfall. You see relatively calm winds across a smaller domain, typically below 5 meters per second. You see a large diurnal cycle and downwelling shortwave radiation. Subsequently, in the temperature component of the buoyancy frequency, you see regular stabilization occurring, which is indicated by these red regions where you have a positive n squared. In the salinity component of the buoyancy frequency, it's generally pretty well mixed during this period, but we can see that during periods of enhanced rainfall, the upper ocean is readily stabilized with respect to salinity because wind speeds are generally pretty calm. And then if we look at the overall buoyancy frequency, we can see there's frequent stable layers forming. And I'll also point out here that rain layer signatures in the salinity component of the buoyancy frequency during this period correspond with instability in the temperature profile. But when we look at the overall n squared, we can see that the magnitude of the salinity stabilization is much greater than the destabilization of the temperature profile. During the MJO disturbed phase here, we can see increasing rainfall, as I alluded to earlier. Winds are still generally pretty calm, but perhaps slightly increasing during this time period. You have a reduction in downwelling shortwave radiation due to increased cloud cover. For this reason, you tend to have less regular and weaker diurnal warm layers forming. However, when we look at the salinity component of n squared, we can see there's frequent, almost near constant presence of rain layers during this period. And subsequently in the total n squared, we can see that the upper ocean is quite stable during the MJO disturbed phase or transition phase. And then finally, during the MJO active phase, during this period, we can see very heavy rainfall. This is evidenced as 2 pulses in this time series associated with 2 convectively coupled Kelvin waves that occurred with this MJO event. You see strong westerly winds, typically above 8 meters per second. You have further reduction in downwelling shortwave radiation. And due to these very strong winds, you generally have a well-mixed upper ocean with only very transient stable layers occurring. Okay, now beginning to look at some of the differences we see between the rain layer and no rain layer simulation. This top time series here is showing across the entire domain mean difference in SST. And the bottom time series is showing again across the entire domain mean difference in net surface heat flux. So looking first at the SST time series, we can see there's not really much of a consistent signal across the MJO suppressed phase. There's just kind of individual events that are imprinting upon domain mean SST temperature difference. But if we look at the MJO disturbed phase and MJO active phase, we can see during the disturbed phase, the domain mean SST is reduced with rain layers across almost the entire period. And if we look at the MJO active phase, we can see SST is increased during this period with rain layers across the entire active phase. And shifting now to look at the net surface heat flux, again, outside of the imprint of one individual event early on in the simulation, there's not really a coherent signal of net surface heat flux difference between the two simulations. But if we look at the MGO disturbed phase, we can see, and you can also see in this table below, that there is more ocean heating and less ocean cooling occurring within the rain layer simulation when compared to the no rain layer simulation. So during this disturbed phase, you have reduced SST with rain layers, but you also have greater ocean heat uptake. So that greater ocean heat uptake during this period is not imprinting on SST. So it has to be going somewhere else, as we'll see shortly. During the MGO active phase, from a domain mean perspective, there's slightly greater ocean heat loss during this period with rain layers that occurs alongside this increase in SST. And so I'll talk a little bit more about why this is occurring. And so again, continuing on looking at these differences between these two simulations, this top figure here is showing a vertical profile of domain mean temperature difference between the rain layer and no rain layer simulation, while the bottom figure is showing domain mean salinity difference between the rain layer and no rain layer simulation. So in the top figure, the brown regions represent higher ocean temperature with rain layers, blue regions represent a lower ocean temperature with rain layers. In the bottom figure, blue regions represent lower ocean salinity with rain layers, whereas yellowish regions represent higher ocean salinity with the solid black contour representing the zero line. And so during this MGO disturb phase, when we said we expected to see rain layers forming most frequently, we can see this evident in the domain mean temperature and salinity differences in the near surface ocean between the two simulations, where with rain layers, you have reduced near surface temperature. You additionally have greatly reduced near surface salinity. So this is just a signature of rain layers showing up from a domain mean perspective and the difference between our two simulations. So to assess how these are affecting air sea interaction and specifically atmospheric convection, I'm going to focus a little more on the domain mean temperature differences between these two simulations. And so accompanying this reduction in near surface ocean temperature during the MGO disturbed phase, we can also see the subsurface ocean is heating in the rain layer simulation relative to the no rain layer simulation. And so in the previous slide where we were looking at the differences in domain mean SST and domain mean net surface heat flux, we could see that the ocean was uptaking more heat during this period. And that heat is accumulating below the base of these rain layers and essentially is isolated from the atmosphere and rain layer presence. So you have this accumulation of subsurface ocean heat that is allowed to persist in the presence of rain layers. And then at the onset of the MGO active phase, you have strong westerly wind bursts, which erode near surface rain layers. And this releases the previously trapped subsurface ocean heat, thus resulting in a warmer ocean column between the surface and depth of about 50 meters. So in this way, rain layers have a direct effect upon SST by reducing SST consistently across the MGO disturbed phase. And they also have delayed imprint on SST by trapping subsurface ocean heat during this period. And then upon rain layer destruction, when that subsurface ocean heat is no longer trapped, you have a relatively higher SST with rain layers in comparison to our simulation without rain layers. And so now, before looking at how this affects atmospheric convection, it's helpful to think about why this subsurface ocean heat is allowed to just kind of stay there and not interact with the atmosphere. And so these time series are showing domain mean salinity component of the buoyancy frequency in the top row, temperature component of the buoyancy frequency in the middle row, and the overall buoyancy frequency in the bottom row for the rain layer simulation on the left and the no rain layer simulation on the right. And what we can see is across the latter portion of the MGO disturbed phase or suppressed phase in the entirety of the MJO disturbed phase. From a domain mean perspective, rain layers are interrupting the diurnal cycle of ocean mixed layer depth deepening. So without rain layers, we can see that there's this regular cycle of the ocean mixed layer depth deepening down to approximately the thermocline at night, and then shoaling with diurnal warm layers during the day. With rain layers during the MJO disturbed phase, that essentially gets shut down. And so that subsurface ocean heat is not readily lost to the atmosphere during this period. Okay, and so now beginning to think about how this might influence the atmosphere, the way I'm going to be talking about this is through contoured frequency by altitude diagrams, which is what you're looking at on the right here. And so the idea behind this is you have vertical velocity in the atmosphere on the x-axis, height in the troposphere on the y-axis. On the right-hand side of the figure, you have upward motion, positive vertical velocity. On the left-hand side, you have downward motion or negative vertical velocity. The dashed contours here show the vertical velocity frequency in the rain layer simulation, whereas the shading shows the change in vertical velocity bin frequency between the rain layer and no rain layer simulation. So the orange shading indicates a higher bin count with rain layers, whereas the purple shading represents a lower bin count with rain layers. And so for this figure, which shows the contoured frequency by altitude diagram and the difference between the two simulations for the suppressed phase, what we can see is some weak evidence that rain layers may be enhancing shallow convection, which is indicated by this orange shading at extreme positive vertical velocity values in the lower troposphere. And then on the other hand, in the middle and upper troposphere, we see largely purple shading indicating there's a lower vertical velocity bin frequency with rain layers at extreme vertical velocities during this period, which would indicate a reduction in deep atmospheric convection. And so now we're kind of going to try and bring it all together. So looking at the bottom, the figure we already looked at of domain mean ocean temperature difference between the two simulations. And in the top, looking at the change in vertical velocity bin frequency in the troposphere. Focus first on the MJO disturbed phase. So again, we have frequent rain layer presence reducing sea surface temperature. Subsequently, in the atmosphere above, what we can see is an increase in vertical velocity frequency at near zero vertical velocities with rain layers, and a decrease at in extreme vertical velocities away from zero with rain layers, indicated by this purple shading at vertical velocities away from zero. And so we term this the direct SST effect of rain layers, wherein rain layers cool the ocean surface, reduce turbulent heat flux into the atmosphere, and weaken atmospheric convection as the MJO transitions from convectively suppressed to convectively enhanced conditions. So this can be thought of as rain layers delaying the arrival of deep MJO convection. Shifting to the MJO active phase, we again have this accumulation of subsurface ocean heat during the MJO disturbed phase. When rain layers are eroded at the onset of the MJO active phase, this results in a warmer ocean column from the surface to 50 meters and higher SST with rain layers. And subsequently in the atmosphere above, we can see this results in a broadening of the vertical velocity distribution throughout the troposphere. And this is evidenced by a decrease in vertical velocity frequency at near zero vertical velocity values in the contoured frequency by altitude diagram, as well as an increase in vertical velocity frequency at extreme vertical velocities away from zero. And so we term this the delayed SST effect of rain layers, wherein subsurface ocean heat that was previously trapped in rain layer presence is exposed to the surface upon rain layer destruction by westerly wind bursts, thus increasing SST relative to the simulation without rain layers and enhancing deep MJO convection during the MJO active phase. Okay, so what does this all mean schematically and how is this happening? So here we're looking Again, at the same figure on the left for the MGO disturbed phase, where you have a cooler ocean surface, weaker convection throughout the troposphere with rain layers. And in this middle figure, the schematic is trying to give an idea of the processes that are driving this phenomena. So during the MGO disturbed phase, you have a colder ocean surface. Thus, you have less intense atmospheric convection, and you have reduced cloud cover. This results in a larger amount of downwelling shortwave radiation upon the ocean surface, as we saw in the difference plot between net surface heat flux between the two simulations. You have a much greater ocean heat uptake during this period, and that's largely being driven by an increase in downwelling shortwave radiation with rain layers. Because rain layers show the ocean mixed layer base, some of this downwelling shortwave radiation is able to penetrate below the rain layer base, warm the subsurface ocean, and that subsurface ocean heat is effectively cut off from the atmosphere by the rain layer. In the no rain layer simulation, you have a warmer ocean surface. This results in more intense atmospheric convection and enhanced cloud cover. So you have less downwelling shortwave radiation impinging on the ocean surface. You have less accumulated subsurface ocean heat. And you have this regular diurnal cycle of deepening of the ocean mixed layer, where subsurface ocean heat is not cut off from the atmosphere for extended periods of time. Now looking at the MGO active phase, again have a relatively warmer ocean column from the surface to 50 meters and more intense atmospheric convection throughout the troposphere. Schematically, looking at the middle of this slide, we can see with rain layers, you have a warmer ocean surface resulting in more intense atmospheric convection as rain layers are eroded by westerly wind bursts. Previously accumulated subsurface ocean heat is released and amplifies the intensity of MGO convection. Without rain layers, you don't have you have a weaker subsurface ocean heat reservoir, so you have a relatively colder ocean surface. You have less intense atmospheric convection during this period. And so with that, to kind of wrap this all up, rain layers reduce SST through cold rain input and prolong SST reduction through stable salinity stratification. Frequent rain layer presence during the MGO disturbed phase effectively decouples the subsurface ocean from the atmosphere above, allows the subsurface ocean to be heated by penetrating shortwave radiation, and for that heat to just kind of accumulate and build over this period. At the onset of the MGO active phase, westerly wind bursts erode near surface rain layers. This releases the previously trapped subsurface ocean heat and amplifies the intensity of MGO convection during this period. And so in the bottom here, I've just included sort of a schematic illustration of our findings that's included in our paper that was recently published in JGR Atmospheres, which I think this QR code should hopefully take you to if you're interested in reading more. And yeah, thank you.
Thanks very much, Kyle. It was comprehensive and great presentation. Any questions for Kyle? Okay. Yeah, go ahead, Sarah.
Yeah, this is really great, really interesting. I wondered a very basic question about the temperature of rainwater. Is it always cold?
Yeah, I think.
And does it vary? And does that affect the results?
Yeah, I think it's often approximated to be equivalent to the atmospheric wet bulb temperature. And so generally, I think it's about a 5-degree difference between the rainwater and the SST. So one shortcoming of our model simulation is that MIT GCM doesn't account for the rainwater temperature. But we did some comparisons between MIT GCM and some previous one-dimensional ocean modeling simulations we did with Gotham that show that the magnitude of stabilization between the two simulations seems pretty consistent.
Thanks.
Thanks, and Kyle. Eric?
There we go, unmuted. What's the magnitude of this effect? You know, I saw a few numbers, like a few watts per square meter, or let's say, how much extra rainfall or something like that?
Yeah, that's a great question. Let's see. Okay. So this is going to be a lot of information. But this table is showing for the suppressed, disturbed, and active phase, the difference in various variables between the rain layer and no rain layer simulation. So from a domain mean perspective. And so some of these differences seem pretty small, like the SST change of 0.03 degrees during the MJO disturbed phase. But this actually represents about 15% of the composite SST range across MJO events. So it's still fairly appreciable, although it's a small number.
Are there circumstances in which you would expect it to be a larger number? You know, is this the place where it's going to be the strongest in the world?
I'm not sure, but I would think it would be strongest here, maybe in the West Pacific warm pool as well. But yeah, I'm not sure if it would be stronger anywhere else.
Okay, thanks.
Great. Thanks, Eric. Thanks, Kyle. Yeah, I had one question, Kyle. In the Indian Ocean region where the MJOs originate, we also have barrier layers, right, where you have different temperature and salinity stratification. Do you know how, like, the rain layer would impact if you have a barrier layer versus if you don't? Like, because the barrier layer also, if you have strong winds that erodes the barrier layer, it releases more heat from below because you have a warmer pool of water sitting below the mixed layer, right, in a barrier layer. If you have a rain layer, are there interesting interactions between the rain layer at the surface and the barrier layer below the mixed layer?
Yeah, I think Elizabeth Thompson's 2019 paper that looks at stable layers that occurred during Dynamo looks at stable layers that occurred during October and November Dynamo MJO events. And during the November event, there's a very strong barrier layer present. In the October event, there wasn't. And I think they found that when the barrier layer is present, you get a stronger salinity gradient following precipitation versus when the barrier layer wasn't present. So you have more stable rain layers. It would be interesting. I haven't thought about if a barrier layer is present, if you would have potentially a greater heat release following rain layer destruction and barrier layer destruction. But that seems like something that could also happen and could further amplify convective intensity.
Yeah. Great. Thanks. Other questions for Kyle?
Does the model include cold pool effects?
How do you mean?
When it's rain, the air is colder, so it makes the heat flux difference, and there are some significant mean effects from that.
Yes, it does include this.
Sarah?
I guess the other thing that struck me is you have this heating below the surface, and I'm wondering if biology would influence how strongly that affected. And is there I imagine this version of the model doesn't include a lot of biology and self-shading, but I wonder what that might do if it were invoked.
Yeah, I don't think the model really includes that. And unfortunately, I'm not really I'm not really sure how that would.
It's a good speculative question for for the future. Maybe the launch of PACE would open some avenues for beginning to think about that.
Tony, go ahead.
Hi, Carl. Kyle, thanks for the very nice presentation. I have a question about the configuration of the couple WRF and MIT GCM. How do you handle the open boundary conditions, both for the ocean and atmosphere?
So like the surface or lateral boundary condition?
Lateral, sorry.
Yes, we had at the lateral boundary conditions had 3 hourly boundary forcing using HICOM for the ocean and AR5 for the atmosphere.
Got it. Thank you.
Thanks, Tony. Yeah, I had another one, Kyle. I was thinking of primary MJO events versus secondary MJO events, right? Like primary MJO events, you don't have much happening in the central Western Indian Ocean, and then you start atmospheric convection, which organizes, and then the ocean is basically primed, and then you have these strong wind events, precipitation from the MJO versus a secondary MJO event where an MJO goes all the way around the globe and then comes back into the Indian Ocean. So the Indian Ocean has already seen strong winds, rain, mixing, all of that. Do you know how like a primary event could influence some of these dynamics compared to a secondary event where you've already had mixing? The ocean has responded to MJO convection and wind mixing.
Yeah, that's an interesting question. I haven't really thought about this, but I would think that with a secondary MJO event, you potentially would have less ocean heat to tap into, since it's kind of following on the heels of a previous MJO event. Now, sometimes I think there's typically more of a lag between a primary event occurring where the MJO kind of doesn't occur for a period and then reoccurs, where I would think that that would allow more ocean heat to kind of build up prior to the arrival of the primary MJO event, and that could potentially further amplify the convection in that case. But I'm not sure. I haven't really thought about that too much.
Great. Thanks. Tony, go ahead.
Thank you. Sorry for another question. So based on your findings, what do you think? Do you think there's anything missing in terms of physics in the subseasonal and seasonal prediction models that are currently being used that tend to have lower resolutions, for example? It's the same system that they use for El Nino and MJO, right? So those models, is anything missing?
Yeah, I would think a lot of those models, the vertical resolution in the ocean is fairly coarse. And I think you're not going to refine or not going to resolve a lot of these features appropriately if you have like 10-meter vertical grid spacing in the upper ocean. So I know there's like some parameterizations out there that are trying to account for this, but I think it's hard to capture the full effect when your vertical resolution is very coarse.
Mm-hmm. Got it. Thank you.
Okay. Any other questions for Kyle? Go ahead, Amit.
Kyle, this is sort of related to the question that Anisha asked, but if you have either strong thermal fronts or salinity fronts, which could be from, off the equator, you could have river water hanging around, for example. How would that change the picture?
Yeah. Well, so typically if you had a freshwater input from river runoff or something, if you have some kind of background stratification in the ocean, that results in enhanced stability following a rain event. So you would have more stabilization within the rain layers. I'm not sure if you had some kind of a thermal front, if that could potentially affect like advection of these features. But I guess my immediate thought would be that with river runoff and freshwater input from that, if you have rain falling on an ocean that already has background stratification, you're going to have even greater stability. So you would need correspondingly stronger winds to erode a rain layer that formed under those conditions.
Right. Yeah, you could have those thermal effects that you talked about hang on for persistently longer time before the winds get strong enough to release that heat.
Yeah, that's what I would expect.
Great, thanks.
Thank you. Great talk, Kyle. Really enjoyed it.
Okay, I don't see other hands raised, Kyle. Yeah, thanks again for an excellent talk. Really informative. So thank you.
Yeah, thank you
Thanks
very
all.
much. Really great.
Yeah, thank you so much for having me, and thanks for all the great questions as well.
Thank you, Kyle.